right, welcome to class, everybody. Just a reminder, if you want to take the test 3 retake, you guys are welcome to come and take it anytime during my office hours, which are Monday, Wednesday, Friday at 9 a.m. and 1 p.m. So I won't I won't put your grades for the retake into Canvas until after we've finished taking attendance for the rest of the semester, but you're welcome to come and take the retake whenever you're ready to. So here's our attendance sheet for today. I'll let you guys start passing that around. And our lesson for today is about logarithms, which is section, excuse me, section 9.3. So in yesterday's class, we talked about exponential functions, and you can also have exponential equations where you're looking for the exponent. So for example, in this equation, what would x need to be to make this equation true? Okay, yep, that would work. Because if you do 3 times 3, that's 9, then times 3 again is 27. And if you multiply 27 by 3, that does equal 81. And so the exponent in this case would need to be a 4 because 3 to the 4th is the thing that equals 81. So logarithms are what allow us to calculate or solve for exponents, even if there's more complicated equations. Because like this one you can do in your head, since you know what the powers of 3 are, or you can kind of guess and check until you find the right answer. But sometimes you may end up with exponents that are decimals or fractions or things like that. And so logarithms are the things that help us find those. So when you're looking at a logarithm, I usually find it most easy to think about them in exponential form. So when you have log base b of y equals x, what that means is the x that you're trying to find is the exponent that you raise b to in order to equal y. Does that make sense? So like the base of the power with the exponent matches the base of the logarithm. So if we went back to this equation, the way that we would write this exponential equation in logarithmic form is we'd write it as log base 3 of 81 equals x. And we figured out that x equals 4. And so this is called logarithmic form. The first equation is called exponential form. So logarithms basically help us find the exponents when we have a variable in the exponent. Any questions on that so far? Okay, so let's go through some examples then. So on this one, if we were asked to find x and x equals log base 9 of 81, it may be easier to think about this if you rewrite it in exponential form. So the base of the logarithm is a 9, which means that the base of my power is going to be a 9. Logarithms calculate exponents. So since the logarithm equals x, I'm having the base of 9 raised to an exponent of x, and I'm looking for when that equals 81. So in this case, what would x need to equal? 2. So this logarithm, if you calculate it out, would equal 2. So why don't you guys try this one? What would be log base 10 of 100,000? Once you've got your answer, give me a thumbs up, just so I can see where you guys are at. All right, everybody call it out. What did you guys get as your answer on this one? Or maybe you guys don't know yet. Okay, so in the logarithm, what is the base? 10. Okay, so we're looking for what would the exponent of 10 be to equal 100,000? If we write it in that form, that's a little bit easier to figure out. What would the exponent need to be? 5. Because 10 to the 5th power is 10 times itself 5 times, which would give you 100,000. So this tells us that X equals 5. Any questions on that so far? Okay, let's try another example. So on this one, what is the base of our logarithm? 7. And the logarithm calculates the exponent. So in this case, our exponent is going to be X. And we're looking for what exponent do we raise 7 to make it equal 1. And, oh, yep, you guys said it. Good job. X equals 0, because anytime you raise any number to the 0 power, it will equal 1. And so in this case, X is going to equal 0. Let's do a quick check-in. Scale of 1 to 5. How are you guys feeling about logarithms? Okay, awesome. Cool. So let's do another one then. On this one, we have log base 16 of 4 equals X. So go ahead and write on your paper what this would look like in exponential form. And if you want to, you can also find the answer, but start off by writing it in exponential form. All right, someone raise your hand and tell me, how would you write this one in exponential form? Oh, yeah. Perfect. Okay, awesome. So in this case, any ideas of what X could be? Yeah.
Could be like 1/2 or like 25.
Yep, that's exactly right. X in this case equals 1/2. And one way you can think about this is you can say, well, I know that it has to be in between 0 and 1, right? Because 16 to the 0 would equal 1, 16 to the first power equals 16, and 4 is in between those two outcomes, either 1 and 16. So I know that it has to be a fraction between 0 and 1. And then how did you know specifically that it was 1/2?
I kind of just did it in my head where like reverse root 4 squared is 16. So I just like, rather than having it be squared, I just did it 1/2.
Okay, perfect. Yep. Yeah, because fractional exponents represent roots. So a exponent of 1/2 is the same thing as a square root, which, just like you said, is kind of like the opposite of squaring it. So does that make sense to everybody? Like why this would be 1/2? Because you can think about the you can think about 16 to the 1/2 power as the square root of 16. And the square root of 16 does equal 4. And so that tells us that our exponent would be 1/2. If it was a cube root, you would have your exponent be 1/3. If it was like a 4th root, you'd have 1/4, and so on. Any questions on that one? So remember, roots correspond to fractional exponents. So if you know that you need to take the square root, then you would make your exponent a fraction, like 1/2. Okay, let's do another example. So on this one, we have log base 100 of 1,000. So let's write it in exponential form. What would the base of my power be? Perfect, 100. What's the exponent of my power going to be? X. And what's the thing that it's equal to? 1,000. So any ideas on what X could be in this case? Which one are you, sorry, I didn't quite hear what you said. Perfect, 3/2. Okay, perfect. So X equals 3/2. And if we think about this, this makes sense that it could be a reasonable answer, right? Because if we did 100 to the first power, that would be 100. If we did 100 squared, we would get 10,000. And 1,000 is in between 100 and 10,000. So this seems like a reasonable number, but let's double check and make sure it really will work out. So if we do 100 to the 3/2 power, we can think about this as the square root of 100 cubed. Because remember, the bottom part of a fractional exponent tells us the type of root it is. So raising 100 to a half power is a square root. And then the top part of the fraction just works like a regular exponent. And if we do the square root of 100 cubed, does that equal 1,000? Yep, because the square root of 100 is 10, and 10 times itself 3 times will equal 1,000. So sometimes, like in this situation, you may need to take a root and then raise it to a different power. So like on this one, we just took the square root, and so we had an exponent of 1/2. But in this one, we had to take a square root and then cube it. And so that's why we had our exponent be 3/2. Any questions on that? Why don't you guys try this one on your own? So I have log base 27 of 9. All right, so if we write this in exponential form, what's the base of my power? 27, what's the exponent? Okay, and what does that equal to? 9. Okay, so this is exponential form. And when we look at this equation in exponential form, is x going to be greater than or less than 1? Less than, right? Because if you did 27 to the first power, that would equal 27, but we want it to equal 9. So we know that it's going to be less than 1. So we're going to get some fraction in between 0 and 1. But the question is what fraction do we get? So any ideas of what type of fraction we could raise 27 to? Who said it? 2/3. Okay. So if we do 27 to the 2/3 power, we can think about this as the cube root of 27 squared. So what is the cube root of 27? 3, right? Because 3 times 3 times 3 equals 27. So the cube root of 27 would be 3. So we can think about this as 3 squared. And does 3 squared equal 9? Yeah. So in this case, our variable that we're trying to find, or x, would equal 2/3. So log base 27 of 9 equals the fraction 2/3. So when you have these ones where it's going to be a fraction, what I would recommend is first of all, figure out what type of root you need in your fraction. So like when I look at the 27, I say, okay, well, I know that 27 is a perfect cube because we've worked enough with exponents to know that 3 to the 3rd power equals 27. And so I'd say, I know that's a perfect cube. So I would start off by just taking the cube root of 27. I'd say, well, that equals 3, but I want my output to equal 9. And so I'd say, okay, well, if I do 3 squared, then that will equal 9. So I kind of figure out this part of my fraction first, and then I figure out what the top part needs to be. Any questions on that? That's you. All right, let's do a check-in on this. So scale of 1 to 5. How are you guys feeling about finding fractional answers to logarithms? Okay, awesome. So let me show you the type of stuff you're going to see on your homework. So some of the problems on your homework, they'll give you an equation like this. You don't need to solve for anything because there's no variables, but what they'll ask you to do is rewrite it in logarithmic form. So in this case, what would the base of our logarithm be? 4. And then I would take log base 4 of what number? Yep, 6c4, and this would equal 3, because remember, logarithms calculate out what the exponent would be. And in this case, we know what the exponent is. We know the exponent is 3. So the log form of this equation is log base 4 of 6c4 equals 3. Because the way that logs work is the base is determined by the base of your power. You take the log of the thing that the power equals, and then that will give you the exponent for the power. Any questions on that? Okay, so you'll have some like that where you're asked to write it in logarithmic form. You'll also have some where you're asked to rewrite it in exponential form. So we've been doing this a lot because this is kind of how we solve logarithms. But on this one, what would be the base of our power? 10. What would be the exponent of our power? 4. And the thing that it's equal to? 10,000. So this is actually the majority of your homework, is being able to convert between the two forms. So we've been doing this one a lot, so I'm not going to practice that, but let's practice rewriting this into logarithmic form. So go ahead and write this down on your paper in logarithm form, and then I'll show you what the answer is. You can check your work. All right, give me a thumbs up if you got this as your answer. Okay, awesome. Cool. So you'll have a whole bunch of questions like that. And then you'll also have a couple questions where you're asked to graph a logarithmic equation. So remember, a graph just communicates the infinite number of solutions that you have to an equation. So you can think of the equation in logarithmic form, or you can think about the equation in exponential form, which is the way I personally prefer to think about it. So if we were to rewrite this equation in exponential form, what would be the base of our power? 7. What would be the exponent? Y. And what would be the thing that it's equal to? X. Perfect. So if we want to find some things that make this equation true, let's just make an XY table. And typically we usually choose numbers that are easy to plug in for X. You know, like that's usually how we find equations. But in this case, I think it might be easier if we decide some numbers for Y. So I'm going to say, like, what if Y is 0? What would X need to be? 1. If Y was 1, what would X need to be? 7. If Y was 2, what would X need to be? 49. And that's not going to be on my graph, but it will give me a good idea of where my graph should go. So if X is 1, then Y is 0. So that's going to be this point, this point, this point, and this point. So I can automatically eliminate these two graphs because those don't have X is 1, Y is 0. Because this one, I kind of covered it up a little bit, but see how that graph doesn't go on like X is 1, Y is 0. So I can eliminate those two from my first point. Then for my next point, when X is 7, Y needs to equal 1. So that's going to be this point and this point. And we can see in this first graph that that point is not on the graph. And so that means that this would be our correct graph of the equation. And if X is 49, which is going to be like way far to the right, then Y would be 2, which makes sense because if you look at how the logarithm graph is growing, it's not growing very quickly. Like it's kind of like it won't flatten out ever, like it will keep going on forever, but it's going to grow really, really slowly. Which makes sense because logarithms and exponential functions are inverses of each other. So in yesterday's lesson, we learned about exponential functions where the graph looks more like this. And logarithmic equations are kind of like the opposite of it. So in exponential functions, you grow really quickly up to either positive Y or negative Y, and then you kind of flatten out at 0. With logarithms, you flatten out along y is 0, and you grow towards the x-axis, like that part grows really big. So it's kind of like the x and y axes switch when you compare logarithms to exponential functions. Any questions on how to graph logarithmic equations? Okay. So you'll have some graphing problems. Let's do one with a fraction, just so that we can look at how that would work. So in this case, we have y equals log base 1/3 of x. So what would be the base of my power if I were to rewrite this in exponential form? Okay, 1/3. What would my exponent be? Y. And my thing that would be equal to would be x. Perfect. So what are some solutions that would make this true? Okay, 0 for x or for y? Okay. Perfect. Okay, so when y is 0, x has to be 1. What would be another easy number to plug in? Okay, -1 for y, I'm assuming. Okay, so if y is -1, then you basically do the reciprocal of 1/3, which would be 3, because that's what negative exponents do. And then exponent of 1 will just raise it to the first power, which would give you an output of 3. You could also do an exponent of -2, which would find the reciprocal of 1/3, which is 3, and then square it, and you would get x equals 9. So if we graph this, if x is 1 and y is 0, that gives us these points right here. And so I can automatically eliminate these two, which also makes sense because those two graphs are shaped like exponential functions. So they're not going to be logarithmic functions because they're shaped kind of like what we worked with yesterday. Then to figure out which one of the remaining two graphs it is, I'll just look at my other solution. So if x is 3, y should be -1. So I should have this point on my graph. And so that means that this is the correct graph of that equation. Any questions on that? Okay. One of the places where logarithms are used a lot in real life is when we measure earthquakes. So when we measure the magnitude of an earthquake, it's measured on a logarithmic scale. And T is a measurement of basically like, so like on a seismograph, they have like really sensitive equipment that measures like how much like their, I don't know exactly like the mechanics of it, but basically they have something that measures how much something moves. And they do it in like a very, very precise way. And T is the number that describes how much it moves or how much it vibrates. Because like an earthquake, obviously if the earth is shaking, then your equipment that's resting on the earth will also shake. And so if T, which is the measurement of like how much it shakes essentially, if that equals 1,000, the magnitude of the earthquake is calculated as log base 10 of T. So on your homework, you'll have a couple word problems where they'll give you this equation for the magnitude of earthquakes. And we'd say if T equals 1,000, then I can just find the magnitude by finding log base 10 of 1,000. Might be easier to think about this in terms of exponential form. So I could rewrite this as 10 to the m power equals 1,000. And what would m have to be in that case? Yep, it would be 3, because if you do 10 times itself 3 times, that will equal 1,000. So the magnitude of this earthquake would be magnitude 3, which so not a very serious earthquake. But if an earthquake has magnitude 7, the question is how many times greater is the shock wave than the smallest shock wave measurable on the seismograph? So like the T is measuring how much like greater the shock wave is. So they're basically asking us to find T if the magnitude equals 7. So we can say 7 equals log base 10 of T. It might be easier if we think about this in exponential form, and we can write this as 10 to the 7th equals t. And what does that mean that t is? I think it's 10 million, whatever 10 to the 7th is. The 7 zeros. Yeah, that'd be 10 million. Perfect. Yep. So that's one practical application of where logarithms are used in real life. So you have earthquakes. And then the last few questions on your homework will ask you to find inverse functions of logarithms. So if we were to graph this function, you know, it would look kind of like those graphs we were graphing earlier. And the inverse of a logarithm function is an exponential function. It was a little while ago that we did inverse functions, but do you guys remember how to find them? I think it was actually even like unit 1, maybe. You guys remember? Mm-hmm. Yep, exactly. So like if you had a function like f of x, I'll do like a really easy one. If you had like x plus 5, the way that you would find the inverse function is you're basically trying to find the function that undoes the original function. So you write the function in terms of y, and then you switch the x and the y's, which would give you x equals y plus 5, and then you solve for y. So you like subtract 5, which tells you that x minus 5 equals the inverse function y. And so you'd get something that looks like this. And this function undoes this function, essentially. So that was something we learned back in unit 1. And the process for finding the inverse function of a logarithm is the exact same way. And your answer will pretty much always be an exponential function because logarithms and exponential functions undo each other. So first of all, we'll rewrite this equation with a y, and we'll write this function as y equals log base 4 of x. And then to find the inverse function, I'm going to switch my x and my y's. So I'm basically making a new function where x equals log base 4 of y. And if I want to solve for y, like get y by itself, the way that we do that is we write this in exponential form. Because if I write 4 raised to an exponent of x, that gets y by itself. Does that make sense in how we do that? So the inverse function of f, which we write like this is going to equal 4 to the x power. So let's do one more example of that, and then I'll let you guys get started on your homework. So try this one on your own. So to find the inverse function, first of all, write it with a y, and then switch the x and the y's and solve for y. All right, so when we switch the x and the y's in this case, we get x equals 6 to the y. And if I want to solve for y so that I can find the inverse function, I can rewrite this exponential form in logarithmic form. And I can say log base 6 of x equals y. Because remember, logs always calculate out what the exponent is. And so this makes it so that y is by itself. And so my inverse function is going to equal log base 6 of x. So that's everything you need to know to be able to do your homework. So I'll let you guys go ahead and get started on that. If you have any questions on this or any of the previous homework assignments, let me know. And I'll let you guys get started. And was there anyone who didn't sign the attendance sheet?